Reality behaves differently when it knows it's being watched. That sounds like philosophy. It isn't. It's physics. And not fringe physics either. This comes straight from experiments that still work every single time we run them. For over a century, scientists have tried to explain this away, soften it, or quietly redefine it. But no matter how advanced the math gets, the same problem keeps coming back. The act of observation doesn't just reveal reality, it changes it. And once you really understand what that implies, it becomes hard to say whether we're discovering the universe or participating in it. And the deeper physicists looked into what observation actually means, the stranger things started to get. When most people hear observer effect, they imagine human eyes, awareness, maybe even consciousness influencing reality. That idea gets mocked a lot, and officially, physics doesn't say that, at least not directly. What it does say is simpler and more unsettling. At the smallest scales, you can't measure something without disturbing it. There's no neutral way to look. To detect a particle, you have to interact with it, usually by hitting it with a photon. And that interaction physically changes what you're trying to observe. If you try to pin down an electron's position, you scramble its momentum. If you try to track its momentum, its position smears out. This isn't a limitation of our tools or our intelligence. It's built into the structure of reality itself. The universe doesn't let you peek without paying a price. So the observer effect isn't about belief, intention, or awareness. It's about the fact that information has weight. The moment you extract it, the system responds. And that realization was already uncomfortable enough, but it was nothing compared to what came next. The moment everything broke was the double slit experiment. This wasn't supposed to be controversial. It was meant to be simple. Fire particles at a barrier with two openings and see where they land. That's it. When physicists sent light through the slits one photon at a time, something impossible happened. Instead of forming two neat piles behind the openings, the particles created an interference pattern, the kind you'd expect from waves overlapping, not solid objects hitting a screen. Each photon behaved as if it went through both slits at once. That alone was strange, but it got worse. The moment scientists tried to check which slit the photon actually passed through, the interference pattern vanished. Instantly. No delay, no gradual transition. The particle snapped into behaving like a particle. One slit, one path, no wave. Same setup, same particles, same equipment. The only difference was whether the path was being observed. At first, this was brushed off as disturbance. Of course, measuring something affects it, right? But then physicists refined the experiment. They made the measurements gentler, less invasive, barely interacting at all. And the result stayed the same. The pattern didn't fade. It didn't weaken. It either existed fully or not at all. Then came the experiments that really shook people. In delayed choice versions of the experiment, the decision to observe was made after the particle had already passed through the slits. Somehow, the outcome still depended on that future measurement, as if the particle hadn't decided what it was until observation forced the issue. Later, quantum eraser experiments pushed it even further. Physicists erased the information about which path the particle took, sometimes after detection, and the interference pattern came back. Not metaphorically, literally, as if reality itself was waiting to see whether the information would exist. At that point, it became impossible to say this was just about physical disturbance. Something deeper was happening. The behavior of the system depended not on what happened to it, but on what could be known about it. And that's when an unsettling idea crept in. Maybe it's not observation that matters. Maybe it's information. And once that door opened, it refused to close. Once information entered the picture, everything got messy. Because if reality changes based on what can be known, then the next question becomes unavoidable. What exactly counts as an observer? At first, physicists tried to keep it clean. An observer wasn't a person. It wasn't a mind. It was just a measuring device, a detector, something physical that interacts with the system and records an outcome. End of story. Except that explanation never really held, because detectors are made of particles too. They follow the same quantum rules. So do the computers that store the data. So does the lab. So does the planet. If everything is quantum, then where does the chain stop? At what point does a fuzzy probability turn into a single, definite event? This became known as the observer problem, and it split physics into camps that still don't agree. The Copenhagen interpretation basically shrugged and said, "Don't ask." Quantum mechanics predicts outcomes accurately. The math works. The universe collapses into a result when measured, and that's all we need to know. What causes the collapse? Irrelevant. Asking that question, they argued, was philosophy, not physics. Others weren't satisfied. The many worlds interpretation tried to remove the observer entirely. No collapse, no special moment. Every possible outcome happens, each in its own branch of reality. When you observe a result, you're not causing anything. You're just finding out which branch you're in. Clean, elegant, and deeply unsettling. Then there were newer approaches like quantum Bayesianism, which took an even stranger turn. According to this view, the wave function doesn't describe objective reality at all. It describes personal expectation. Reality isn't a fixed structure, independent of you. It's something that updates when experience happens. Same equations, completely different meaning. And here's the uncomfortable truth. Despite a century of debate, no interpretation has won. They all predict the same experimental result. They all work. And none of them explain what an observer actually is. In recent years, this tension has only grown. More physicists are leaning toward information-based interpretations, where reality isn't made of particles or waves, but of relationships and correlations. What exists isn't a thing. It's a pattern of information shared between systems, but that just sharpens the question. If reality depends on information, who or what is that information for? And once that question is asked, physics starts backing away slowly. This is where everything bottlenecks. The measurement problem, the one issue that refuses to die, no matter how many papers get published or how advanced the math becomes. On one side, you have the equations. They describe reality as a smooth, continuous wave of probabilities. Everything evolves calmly, predictably, following precise mathematical rules. No jumps, no breaks, no surprises. On the other side, you have experience. You never see probabilities. You see outcomes. One position, one result, one event. The wave doesn't fade into reality. It snaps. That snap has no place in the equations. For decades, physicists tried to patch the gap. Maybe measurement is just another interaction. Maybe large systems behave differently. Maybe the environment washes out quantum weirdness. This led to decoherence, one of the most successful ideas in modern physics. Decoherence explains why quantum systems start to look classical when they interact with their surroundings. The environment entangles with the system, spreading information so widely that interference effects become impossible to observe. From our perspective, the system appears to collapse, but here's the part most explanations quietly skip. Decoherence explains why outcomes look definite. It does not explain why one outcome happens instead of another. The probabilities are still there, hidden, smeared into the environment. Nothing in decoherence selects a single result, so the core mystery remains untouched. Why this outcome? Why now? Why this reality and not all the others the equations allow? After nearly 100 years, physics still doesn't have an answer. Not a real one, not one everyone agrees on. The equations describe what can happen with stunning accuracy. But the moment something does happen, the math goes silent. And that silence is loud, because it suggests that something fundamental is missing from the description. Not a particle, not a force, but a principle that connects possibility to experience. And once physicists realized that, the conversation drifted into territory most of them would rather avoid. That forbidden territory has a name most physicists avoid saying out loud: consciousness. Not as an answer, not as a solution, but as the thing that never quite goes away. Early on, some physicists noticed the problem immediately. John von Neumann pointed out that if you trace the act of measurement step by step, you never actually escape the quantum world. The particle is quantum. The detector is quantum. The measuring device is quantum. The observer's brain is quantum. There's no clean place where probability suddenly turns into fact. This became known as the von Neumann chain, and it leads to an uncomfortable implication. If nothing in the physical chain causes collapse, then either collapse never happens, or it happens somewhere outside the chain entirely. Eugene Wigner took that idea seriously, at least for a while. He suggested that conscious awareness might be the point where possibilities become realities. Not because the mind has magical powers, but because experience itself is singular. You don't experience probabilities, you experience one outcome. That idea made people nervous. It still does. So physics quietly moved on. Consciousness was removed from the equations. Not solved, just excluded. The math kept working. The predictions stayed accurate. And everyone agreed not to talk too much about what was missing. But removing consciousness created a strange vacuum, because the observer never stopped existing. The equations still required one. They just stopped defining it. Today, most physicists will tell you consciousness has nothing to do with quantum mechanics. And maybe they're right. But when pressed to explain why reality produces a single experience instead of a superposition of them, the answers become vague. The language shifts. The confidence drops. What remains is a gap. Physics describes how systems evolve. It describes probabilities with astonishing precision. But it does not explain why there is something it is like to observe an outcome. And that's not a spiritual question. It's an empirical one. Why does reality feel like anything at all? No equation answers that. And the moment you acknowledge it, you're forced to consider a possibility that makes everyone uncomfortable. Maybe observation isn't just a passive act. Maybe it's a necessary ingredient for turning the abstract into the actual. Not control, not creation, participation. And that idea changes the shape of the conversation entirely. So the observer effect isn't proof that consciousness controls reality. It isn't evidence that the universe bends to belief or intention. And it isn't a loophole for wishful thinking. What it is a reminder that reality isn't independent in the way we once assumed. At the deepest levels, the universe doesn't reveal itself from a distance. It responds to interaction. It changes when information is exchanged, and it refuses to be fully defined without participation. Physics can tell us what outcomes are possible. It can map probabilities with incredible precision. But the moment one of those possibilities becomes your experience, the equations stop short. Something else takes over. Something that turns abstract potential into a single, lived moment. Maybe that's all observation ever was. Not a spotlight aimed at a finished world, but the process through which a world becomes specific. Not creation, but selection. Not control, but involvement. And if that's true, then the observer effect isn't just a strange feature of quantum mechanics. It's a quiet hint about the nature of reality itself. A suggestion that the universe isn't something you're merely inside of. It's something you're in constant dialogue with. And the moment you stop thinking of yourself as separate from it, the question stops being whether observation changes reality. The real question becomes what reality would be without observation at all.